We will now start discussion of coupling of different effects and properties. And by coupling, I will consider two different distinct things. One is coupling of, for example, such as a piezoelectric, where we couple mechanical and electrical variables, and the other one will be coupling where we have that, for example, stress is present in material at the same time as temperature changes, and therefore we can have in this particular case that charge density is affected both by temperature changes and the pressure. And it's this second term that we will mostly discuss in this section, and which is very important for applications. So what I'm writing here are thermodynamic equations. For example, let's look at properties such as strain and charge density. Now, how can we get a strain in a material? Well, we can change temperature, that's thermal expansion. We can apply pressure, this is Hooke's law, and we can apply electric field, which is a piezoelectric effect. For charge density, if material is polar, then by changing the temperature, we change polarization. That will produce some charge, current, voltage. We can do it by converse piezoelectric, by direct piezoelectric effect, and we can do it by applying electric field, which through permittivity will produce, by polarizing material, will produce some charge density. These can be described very conveniently through so-called Heckmann's diagrams, and I would like you to be aware of this. They can let me just go back here and say that in each of these cases we can add magnetic fields in magnetization. We can also add nonlinear terms. These are all, as you can see, linear equations, but we can add higher order terms, and we will do that later on, at least for electromechanical coupling. So for entropy, strain, stress, temperature, the electric displacement, and electric field, we can construct the following Heckmann's diagrams, and then you can make them in 3 dimensions if you add magnetic fields and so on. So here we have a stress, temperature, and field, and here we have a effect that connect variables of the same nature. So these are electric, these are mechanical, and these are thermal: entropy, temperature, strain, stress, field, displacement. And then these cross terms are the ones that are giving us coupling of electrical and mechanical, thermal and electrical, and mechanical and thermal variables. So these would be our diagonal elements, and these would be cross terms. So you can make a link of everything with everything practically, and that's very important. So please look at this a little bit, and here you have a coefficients that link these different variables and fields. Now, let's make one example to illustrate why this is important for applications. And by coupling here, I mean mostly that we have two different variables that are present at the same time, in addition to coupling variables of a different kind. So for example, here, if we don't have any electric field in the material, but temperature can change and the pressure can change, then we can have that charge is produced on the surface sample if symmetry allows that, by temperature changes, if material is polar, and by pressure. So what we have here is piezoelectric material. This plus should go here and not there. And so if this material is piezoelectric, when we apply pressure, we will produce some charges on the surface of this sample. This should also go on yellow. So the pink arrows illustrate pressure, and the green blocks are just contacts, for example, metal contacts or some other type of contacts by which we apply pressure, and the yellow is a piezoelectric material. So we apply pressure, we will get change of the state of charges at the surface of the sample. And at the same time, we can allow some heat to come on the sample, and that will also change its temperature. So we will have two terms that can contribute to the to this total charge on the surface of the sample. So if we look at the pressure, this here should be pressure. If we apply pressure, which is sinusoidal function of time, and we look at the charge, if we have only piezoelectric effect, this should be also sinusoidal function, but it is disturbed. It's not exactly sinusoidal. So what's going on here? Well, we have the temperature in the room is also changed while we are doing piezoelectric experiment. It's changed in an irregular fashion, and this charge that we get from the piezoelectric material is modulated by this term here. So this is sigma. This is d. As a function of time, you would get a sinusoidal charge if we have only normal piezoelectric effect, but because of random fluctuations of the temperature, we get these drifts and noise. So if we plot total charge that we measure on the surface of a sample as a function of pressure or force, we should get a straight line. Remember our definition of the piezoelectric effect: response as a function of the field should be a straight line. Here we see that, yeah, we have something straight, but it drifts with time. This actually goes up and down, and there is some hysteretic behavior. And that's because of this term, which is piezoelectricity. So you see the force doesn't change. Force is constant, but charge changes. And this is a big problem if we want to use this material as a sensor. And so what do? We know piezoelectric coefficient. We apply unknown force, and so we are looking at the force that we are applying. We measure response, in this case charge, and from this relationship. We know this, we can calculate force. That's how sensors, piezoelectric sensors work. But here it is not possible. If we measure charge in this particular case, we will have that one charge corresponds to different forces, and therefore we cannot do this. So it's important while you are using a piezoelectric material as a sensor or as actuator to keep all other variables under control, either zero or constant, or if they vary, to know how they vary, so that you can track down from that the actual value. Now you will notice here that I'm plotting two curves in a charge versus force relationship. The blue one is PZT. It's a ferroelectric material, which is also piezoelectric. And that material has a polarization and therefore has this problem if temperature is changed during the experiment. And here you have in red, you have a quartz. And that's a nice straight line. And the experiment is done under exactly the same conditions as the first experiment with the PZT. And here there is no, there is neither drift in this direction, and there is no this hysteresis that you see in a PZT. So why quartz is giving us nice straight line, ideal piezoelectric effect, and PZT, ferroelectric ceramic, doesn't? First, I should explain why quartz is going down and ferroelectric material shows charge going up with the force. That's simply for a convenience, so that you can see both traces. Piezoelectric coefficient of quartz would also do like this. Actually, what I did was just to turn the sample upside down, and that comes to this question I have asked you with in introduction: what happens if you turn sample upside down? So why quartz doesn't have this temperature dependence? Well, it doesn't have it because it doesn't have polarization. It doesn't have a permanent polarization as ferroelectric materials have. And the temperature that I'm applying here is too small to induce some meaningful temperature changes in the piezoelectric effect. When we are discussing piezoelectric experiments, we have to take into account full piezoelectric constitutive equation, meaning that we have to take all terms that may contribute to the final response. In the previous case, I would have here also, in this case, Pi times delta T, that is pyroelectric effect. But as I said, we usually neglect that because we can control temperature in a room and work under isothermal conditions. So I will not consider temperature here, but we will consider both electric field and mechanical stress, and electric field in this pair of equations. So we consider both electric field and stress, and this here should be eliminated. So I will now, you can use any of these four sets of constitutive equations, depending on which one is most convenient for your experiment. And now I would like to show you one specific example of how why you have to use the full constitutive relationship, and how you can get a lot of information about your system. So we have a piezoelectric effect, but you cannot just take and consider this equation. You have to see the totality of the stresses and fields which may appear in your sample, even if you are not applying it yourself, but they may rise in your system because of the boundary conditions that you have there. So we will, for our problem that we are going to consider now, this pair of constitutive equations is the most convenient. So what do we have here? We have a piezoelectric thin film given in green, deposited on some substrate, which is given in blue. And we will imagine that this substrate is infinitely rigid or infinitely thick, and that it cannot deform. This is idealization of a problem. All substrates will be able to deform, but for the sake of argument, we will assume that it is completely rigid. And this example is taken from the paper of Lefke in, I think, Journal of Applied Physics in 1994. So we have a piezoelectric material here. We have substrate, and we are applying pressure that comes perpendicularly to the sample. Okay. Now, when you apply a pressure, since we have a support for the sample will try to expand in this direction. That's just through Poisson ratio that you have in mechanics. If you press something, it will have a tendency to increase to other dimensions. It doesn't have to happen. Sample can shrink or expand in all dimensions, but we will not discuss these other more exotic cases. So the sample will try to expand, but if substrate is infinitely rigid, it will not be able. Now, because of the Poisson ratio, sample has tendency to expand, but it cannot. It remains of the fixed side, and the effect of that is that there is actually the pressure acting on the sample, which prevents this expansion. This happens if you have a sample which is much thinner than the substrate, which is mechanically rigid. Then you have to take into account these pressures, forces that come as a reaction on the film from this pressure sigma 3. And that's not a pressure that we are intentionally applying, but it's a reaction of the system, result of the boundary condition, which tells us that the substrate itself cannot deform. So we write these two equations, and now we know that the strain here is the coordinate system in which we consider this. So z-axis is up, 3 axes, and x1 and x2 are in the plane of this substrate. So for example, x1 will be like this, and x2 will be in this direction. So strains epsilon 1 and epsilon 2 by boundary conditions must be equal to 0. And these are the stresses that are acting on the film, sigma 1 and sigma 2, which are these reactions of film on rigidity of the substrate, and application of sigma 3. And we have sigma 3. While the charge, even though we are applying only this part ourselves, these stresses that react on sigma 3, we will get a longitudinal piezoelectric coefficient, but we will also have these two stresses, these two piezoelectric effects which come from this stress sigma 1 and also one which is perpendicular to the plane of the paper, which is sigma 2. So this will be the total charge. And from this relationship here, we can find what is sigma 1, and we can replace it. We can replace it there and then calculate from the proportionality between pressure and the displacement piezoelectric coefficient. So we can here eliminate sigma 1 from this relationship here. And we obtain, if you do that, and I suggest that you do this calculus of this exercise, which is really very simple, what we get that effective piezoelectric coefficient of such film is equal to D33 coefficient of the film. So I should write here subscript F of the film. So that's what you would have. This is what you would have if your film is not lying on, is not fixed to the substrate, and minus this term over here, which is a function of properties of the film, D31 transverse effect, S13, S11 plus S12. Now it turns out that D31 is negative, S13 is also negative, and this whole term is positive, this is positive, and therefore effective piezoelectric coefficient is always smaller than coefficient of the sample if it was free to expand. So what this tells us is that we can never have in a thin film with a rigid thick substrate as good piezoelectric response as in a free film or in a bulk ceramic, if substrate has this effect and if it is perfectly rigid. This factor here will reduce the total piezoelectric coefficient by at least factor of 2 or even more. So it's a substantial reduction of piezoelectric properties of thin film with respect to those of bulk material, if you look cases where you have this rigid substrate. If substrate can move, can deform under this pressure sigma 3 that we are applying, then situation becomes a little bit more complicated. We will also have forces in the substrate, and this is nicely described in this paper here at EPFL. And then we have to add to this relationship that we derived before, and you can try to do that. We have to add this term over here, which depends on properties of the substrate. So the index S here, substrate S here, actually mean coefficient of the substrate. So you have one term which is reducing, another term which is increasing the effect of piezoelectric material. So if you have a substrate that deforms really a lot, you may have that effective piezoelectric coefficient, that's this whole term, effective, okay? That effective piezoelectric coefficient may be many times bigger than true ferroelectric piezoelectric coefficient of our film. And this can especially happen if you have bending. So if you have a thin film deposited on a substrate, which is also thin, and you bend them, then you would get a huge a huge equivalent or effective piezoelectric coefficient much bigger than you have in piezoelectric ceramics.